Okay, so let's carry on with this thing about Mclarty's chapter on the basics of Topos theory. A power object is an exponential object where we've got the subobject classified to the power of a and its corresponding evaluation arrow. Now, we can sort of get an internalized membership relation here. So this is pretty cool. So we'll see what this means in a minute. But the basic thing is that we get this, we have this arrow, which is in to the power of a, and basically this is the pullback of true along this evaluation arrow of the power object. But more precisely, we don't just pull back over the evaluation arrow, we pull back after the evaluation arrow after this twist. Okay, just to make the things match up properly. So because of this, we're going to have that E, so the twist is P2, comma P1, so we have the E after P2, comma P1, operating on some generalized elements, so a T element X of A and a T element H of omega to the power of A. We have that doing E after the twist on that is equal to true if and only if X comma H is in this into the power of A relation here. That just comes from the basic point that this bottom horizontal purple arrow is the classifying arrow of into the power of A. Okay, but what's it all mean? Well, the meaning is sort of given by this result, theorem 13.7. So suppose we have an arrow omega from A to, sorry, we have an arrow little omega from A to the subobject classifier. Now, that's equivalent to this arrow omega after, well, I'll call it W actually. So it's not confusing. So we have this arrow W from A to omega, that's equivalent to an arrow WP2 from 1 times A to omega, which is equivalent, taking the transpose, we get the name of W, which is the transpose of W after P2. And that's just going to be a point of omega to the power of A. Now, what is omega to the power of A? Well, I mean, think about in set, it would be the set of functions from A to omega, where omega would just be the set true and false. So basically points of omega to the A can be thought of as names of functions, if we like, and then such functions basically correspond to subobjects. So that's kind of why in set theory you call the power sets 2 to the power of x, because you can think of it as the set of functions from the set x to the set 2, which is the set of 2 elements, say true and false. Okay. Anyway, so when you think of this W dash thing as like a sub-object of A, if we like, this name of W here. Anyway, basically then we see that this in to the power of A works like a kind of internalized membership quantifier, because theorem 13.7 says that for any point of A, we have that x is in to the power of A, W, which is just shorthand for saying x comma name of W is into the power of A. Well, we have that holds if and only if this point here, x, is in the sub-objects classified by W, as in it's in W star. So that's what the theorem says. Now, if everything below here is sort of proof, so we just remember then that that's equivalent to saying that EA of W dash comma X is true. Notice I swapped the order because of that twist. Anyway, that statement there at the bottom is equivalent to saying that the outer perimeter of this diagram commutes. Because T after exclamation mark A after X is just T. All right. Now notice that in this diagram, this region on the left commutes, as I demonstrate here, and this region on the right commutes, as I demonstrate in this orange here. And so it follows that E after name of W comma X is equal to W after X. So we have that this red statement's true if and only if WX is true. Now, W here is an arrow into omega, so using the sub-object classifier, and I mean W is the classifying arrow of W star, so we have that WX is true if and only if X is in W star. So we've proved the result. So yeah, this is basically saying that, let's go back here, what we get by doing this pullback is this kind of internalized membership quantifier, and that's the sort of relation, and X and the name of W are in that relation if and only if X is actually a point of the sub-object W star, which is the kind of sub-object that this classifies. So there we are. Now, let's carry on. We'll go on to talking about universal quantification now. So, one observation then is that the name of TE, where TE is actually T after exclamation mark E, the name of TE represents the kind of maximal subobject of E. So how can we see that? Well, the name of TE corresponds to TE, and then that's the classifying arrow of 1 of E. Okay. Right, now for something new. Notice that this TE here, and sorry, name of TE, is itself a monic, okay, because it's an arrow from a terminal object. So it has a classifying arrow, and we call that classifying arrow for all E. Okay? And this is sometimes called, well, it's related to universal quantification. Okay? Now here's the thing about this. Let's consider another point. So let's consider a subobject of E. Now we can represent that as an arrow from E to omega. Equivalently, we could represent it as a name of an arrow from E to omega. In other words, we can represent it as a point of omega to the power of E. And now, if we have that for all E, name of X is true, that's equivalent to saying that name of X is in T of E. And since these are both arrows from terminal objects, that's equivalent to saying X, name of X is equal to T of E. Which is equivalent to saying that this name of X corresponds to the maximal subobject of E. Okay? And I think you can probably do something more general if you consider this to be a general arrow into omega E. You can maybe think of it as a sort of collection of subobjects, and then I guess you'll have that's in name of TE when everything in that collection is a full subobject. Okay, but I need to think about that more. Now, here is a relation. Okay, so this is just a monic into B times A. Now we define the universal quantification of R over A, which is written as for all A in brackets R. I'll just call it for all AR. Okay. And that's defined to be the pullback of the name of T along the transpose of the classifying arrow of R. Like so. Now, equivalent way to define for all of AR is as the subobject classified by for all A classifying arrow of R. And we can see that by this kind of pullback here, by this diagram. Because we know that the right square is a pullback. And so we'll have that the left square is a pullback if and only if the whole thing's a pullback. So, for example, if we assume that the left square is a pullback, in other words, if we assume this kind of definition of for all AR, then we get that the whole thing's a pullback. So we get that for all AR is the pullback of T over for all A transpose of classifying arrow of R. And conversely, if we say for all AR is defined to be the pullback of T along this bottom horizontal arrow, then we get that this left square is pullback. So either way works. How are we to understand this result? Well, basically S is going to be contained in this monic for all AR when S is in the relation with A for all A. Okay, so for all A, S is in this relation. So yes, I think the more precise result is that for any monic, for any subobject S of B, we have that S is contained in for all AR if and only if S times identity of A is in this relation R. So if we have A1, A2, A3, S1, S2, S3,